recorded. Okay, so before we get started, just a quick announcement that we're supposed to have a homework due today, and I believe, like, I assume most of you already almost finished. But since I noticed that there's no access for Blackboard yesterday, so so I'm going to just in case that if you cannot submit or for whatever reason, if you have like been affected by this yesterday, so I decided to extend the homework due from today to tomorrow. But I mean, you're supposed to turn it in today anyway. So if you can already turn it in, then you should turn it in today. But just to give you one extra day as a buffer time for the homework. And regarding the presentation, I got several emails asking me about the correctness of the solution. So please give me some time. I need to read through your thing and then so I can make a proper comment. So I will make sure I will reply to your email in the next couple of days. And also, I want to just make sure that everyone understand the instruction, the rules, just in case that is still not clear. So I mean, because we have like 13 groups, there's no way I could put it in one day, right? If I could, I would do it like the presentation in one day. But so since I can't, though, I'm going to separate into 3 days. And for the whoever presentation on the first day, the 16th, uh, of course that you need to come up with some slides to present. But the thing is that after you present, I want to give you some time to maybe you can still ask me the question, or maybe I could possibly give you some feedback during the presentation. So the reason I put the due date for the written part, so for even though that you're going to present on the 16th, for whoever present on the 16th, you don't need to turn in the presentation slides to me. I'm not going to grade the slides or the material you use to present, but rather I'm going to grade the written solution, like how you do it as a homework, like the written part on the 18th. So which means that even you present on the 16th, if between 16 and 18th, based on my comments on during your presentation, or maybe later on you find out that you need some time to write down a more detail, because I can understand that for the presentation you need to fit in time, so you definitely need to cut down a lot of detail, right? Maybe sometimes that you can only put one sentence and you're going to just explain it like orally, right? So I could imagine for everyone that the presentation, the slides will be definitely shorter than, or even much shorter than your written solution. So when I grade your oral presentation, I will see whether you can convey the key message. But I can also imagine that because the presentation, that oral presentation, there's a time like limit, and plus there's only limited information you can show. So the written part is supposed to help you to gain more points in some sense, right? So I will grade your oral presentation, but at the same time, I do not want the oral presentation to be the only thing that I evaluate. So which means that later on, for whoever present on 16th, you will still have 2 days to fix your written part, to write down a more detailed solutions on and then turn it in on the 18th. So you will still have time to fix. Maybe you, after you present, you realize that, oh, this part you didn't do well, or you missed some detail, and then you realize it after the presentation. Then you still have 2 days to fix it and turn it in on 18th. But of course, for people who present on 18th, since you already have 2 days extra than those present on 16th, so to be fair, I will put the written solution due on the 18th. And then, of course, for whoever present on the 30th, I mean, you already have the, in some sense, some advantage on presenting the last. So of course, I would definitely ask you still to turn in your written solution on the 18th. So then you're more or less turning in around the same time as other people. So just to be clear, even you present on the 16th, I would not grade your presentation, the slides, but rather the one of the component for the grade would be on the written solution. And as I said, the written solution is supposed to be like a supplementary things in the sense that like, if you feel like that your presentation is not perfect or there's only limited information you can tell people, then the written solution will be the part where you can show more detail to me. So sometimes that this happens in the past where some students, because the time limit, they owe me some detail or they forgot to mention some detail in the presentation, but they give me a perfect written solution, then they will still gain a lot of points, like the majority of points, because the written solution is correct. So think of the written solution as a remedy if you feel like that you only have limited time or like limited space doing the presentation. Okay, and so, and then just to remind you that after the homework this week due on Thursday, then there will be no homework due next week, because I mean next week is the presentation. So I'm going to like let you write carefully about the written solution, and then also the final homework, the homework 12, will be due the week after the Thanksgiving break. And I'm still going to assign it pretty soon, like in the next couple of days, but I will put the due date to be afterwards. So I want to give out the homework problem as early as possible. So people, whoever already finished the presentation or they want to start early, they could start early. So I need to warn you that the homework 12 is going to be longer than the usual homework because we are going to have like more than 2 weeks on this. So basically you should start earlier because there will be more problem. Probably I could imagine maybe 6 problem at least. So you should definitely start early. Okay, so is there any question about the presentation? I want everyone to just raise the question now so I can just make sure people know the instruction or the rules. Is there any other questions? Okay, so if you have any issue with your presentation schedule, you should let me know. For example, that if for whatever reason you really cannot present, I assume that it's pretty much, I mean, someone has to do it first or someone has to do it last. I cannot fit in the same day. So if you really have like unforeseeable reason that you cannot present or the group cannot present on that day, please let me know. I cannot guarantee I will definitely accommodate it, but I will try to shift around the schedule if there's really a need. But keep in mind, there's another thing I want to remind everyone that the third component of the presentation grade is that not only I'm going to grade everyone the oral presentation part, and then also the written solution, I'm also going to have a small portion as an attendance. And for the attendance, not only I'm going to check whether everyone comes in, I can see it from the Zoom attendance. I also mentioned this in the announcement that everyone should take a note, right? It should not be a very super detailed note, but you can actually just write something essentially just to show me that you did pay attention to what other people present, right? At least you should be able to write down what's the topic, right, of what other people were doing, right? Write some notes so I know you were there paying attention to other people's presentation. And then I will open up a submission of the like attendance notes right after the presentation. I think I said that everyone should turn in by 6:30. I remember I mentioned that. Then I will open that, and then everyone, I will remind you like on the presentation day to turn in the attendance note. So you would remember to turn it in right after the class. So I will open up for Monday and Wednesday, and also the Monday on the 30s. And I will also open up another homework submission. I mean, I will call it presentation, written solution, something like that. I will open it up next week so you can submit it before 18th. Okay, so so if anyone want to just double check, make sure, kind of see whether the written part is okay or not, please like send me your stuff and just say that you want to double check, right? I cannot guarantee I could reply your email right away because I'm getting a lot of email these days, but I'm going to make sure that I could send you things, reply your things like over the weekend. So especially for people who are presenting on the Monday, if you just want to double check that your solution written part is correct, make sure you're not presenting something wrong, then please send me your like something you already written up if you even get stuck in solving some of the problem and you need to talk to me over the weekend or in the next couple of days, then please also email me to make an appointment with me. And for people in group of 2, please take advantage of having a group member. The reason I want to put some people in group is not for you to do it separately. You should definitely talk to each other, like take advantage of having someone you can talk to or rely on in some sense, right? And then even though I ask everyone in the group, like especially if you have group of 2, I ask 2 of you to submit the individual solution like completely, but still you have someone to talk to compare the answer solution, right? And then in some sense your workload is also half, because if you only know solving half of them, then you have the other person to help you on the remaining part, right? So there's an advantage of having a group member. Please think of it as an advantage, right? If you really cannot reach, I hope at this point everyone already have in contact with their group member. If you don't know who your group member is and you cannot contact with that person, you cannot get in touch with the person, please let me know so I can put you in contact with the person. And if you haven't started doing it, then you should definitely start it. There's not much time left, right? So you should try to talk to your group member and then figure out that how to share the workload, for example. Okay. So I hope that this should be equally shared between the group members. I don't want to see like the situation where later on someone come to complain that, oh, I do most of the work while the other person barely do anything. Okay. I mean, well, adults here, we're not in high school or middle school, right? So I'm relying on you guys to know that how to make the workload equally shared. Okay, so yeah, so if there is any other questions for the presentation, yeah, I want to answer now. Yeah, sure.
I had a question. If you're doing like a group by yourself, can you like use slides for like your entire presentation?
Yeah, I think what do you mean can you use slides? I mean, you can use slides.
Like the cameras on my phone isn't working, so I can't present it that way, like written out.
Oh, no, it's fine. Yeah, it's fine. That's why I didn't really mention it at all. Like, so either you can do a completely slides talk, like alone, like throughout the whole presentation, right? So I understand that not everyone has like a tablet or something that they can write on. That's why if you want to use slides, like what I'm going to do now, even you cannot write on the things, that's fine. That's totally fine. But then it means that there may be, when it comes to explaining things, you need to plan out that, okay, maybe you need to, like, for example, like I can imagine that you cannot squeeze or put every single detail, right? So sometimes you might need to maybe like explain it orally, right? And if you use slides, right? And if you don't have and then so I don't want to restrict how everyone presents, because different people have different style. So if you want to do a complete slides talk, that's totally fine. But you just need to kind of like find a way to explain things while people reading the slides, especially if you cannot write on the board. But doing the complete slides talk is fine to me. Yeah.
So if we're doing slides, do you want us to send them to you, or do you want us to like share a screen on
you can
like
share
a tablet
screen,
or
yeah.
whatever?
Yeah, actually, because if you send it to me, it's not going to help you present in some sense, right? Because if you send it to me, then I like when it comes to the presentation day, I mean, of course I can share the screen, and then but then you have no control of that screen, right? So I mean, so yeah, you don't have to send it to me, like unless you want me to take a look at your slides before you present and give you some suggestion. But on the presentation day, like I will give everyone the access to share the screen, so you can share the screen from your computer, and then so you have the full control of how fast you want to do or any effects you want to do, right? Because you need to have a control of the slides when you do the presentation. Yeah. So any other questions? Okay, so what I'm going to do today is the following. So I'm going to finish up the hyperbolic geometry. And I need to give you a heads up that some of the things that in the second half of these slides, you're going to see a lot of like computation, but I don't want everyone to freak out. So the thing is that for this hyperbolic geometry, my focus will be on, like, first of all, you definitely need to know like what's the definition for example, for straight lines in hyperbolic model. So we already kind of talked about a first model, the point colored disk, but I'm going to talk about the model for half plane. So at least you should know like how to draw a straight, what is a straight line, how many types are there, right? And so like the basic definition and property. But when it comes to the computation, I'm going to throw in some formula. Essentially, you just need to make sense of it. But I do not count on, or I do not expect anyone to memorize the formula. So you don't need to like worry that, oh, I have to memorize this and that, like algebra formula. No, it's just for information purpose. And the only use is that later on I may assign some homework based on those formula. So I want people to at least see this part for completeness of the information. So do not freak out if you don't know or if you cannot derive the formula yourself. That's totally fine. Every information, if you want to know how to do it, like detailedly or precisely, it's in the textbook. My slide is more like for information purpose, and then I'm doing a very like kind of in dense summary of the information there. Okay, so that's the first thing I want to emphasize. So let me turn to bigger view. Okay, so like what I said, we already discussed the disk model. So for hyperbolic geometry, technically there's three models that we mentioned in the textbook. But the first one is kind of not ideal in the sense that it's going to change the angles. It's going to distort the angles and the distance. So it seems like we sacrifice both important things. So that's not the very ideal model. The second and third is what our focus here is the Poincare disk model and the Poincare half plane model. So the disk model, essentially we use the disk that you saw here for describing the hyperbolic geometry. So we mentioned on Monday that everything should be inside the disk, while the point on the disk is what we call the ideal points, the infinity, right? So basically, like on Monday, we talked about that there are two types of straight line in this model. So imagine that because I mentioned on Monday that we cannot really draw or create the most rigorous model in three-dimension case for hyperbolic geometry. So it's like you can, if you want to see an Earth on the two-dimensional plane, then the only thing you can do is do some kind of projection for the Earth, right? So that's the globe, the world map that we saw today. But you can imagine that the world map is not really completely accurate, right? Like the distance might distort, or maybe the direction, the angle might distort, right? Or maybe the size of the land might distort. So there's some sacrifice we need to make here. So it turns out that we can also do that to hyperbolic geometry. We do some kind of projection, we make some compromise, and we could use a disk like this to give us a nice model or illustration for the geometry one. And this hyperbolic geometry is totally different than the Euclidean geometry, right? Maybe I should be a little bit careful. It's not completely different. Like there's some shared property, but definitely you will see a lot of big difference as well. It's not exactly the same. So we talk about the straight line in this model. One of them is this open diameter, right? So open means I don't want to include the points in the boundary. Second type is like any open arc like this, where as long as it's orthogonal, like perpendicular to the boundary, right? So this would be a second type of straight line in the model. And we on Monday, we also talk about that we can make sense of parallel in this model. But since we have these two kind of different line, so we have two type of parallel. So first is what we call the sense parallel, meaning that the two lines only intersect on the boundary. So imagine in some sense, like roughly speaking, those two lines only intersect at the infinity, right? So it's as if it doesn't really intersect at all. So as if you have two such straight line, doesn't matter which type, but they intersect only on the boundary circle, but it doesn't intersect or have no common points within the disk, then this is what we call the sense parallel. And the example would be the arc K and the diameter M that you saw here. So let me erase some of the things so you can see the M here. So it's an M and K here. And so it only has one common point on the boundary here. And there's another type of parallel is what we call the ultra parallel. That means they don't share common points at all. So for example, line K and line L here is what we said the ultra parallel here, or divergently parallel. Okay, so we talked about this on Monday, and also we definitely want to check because how do we come with, how does the hyperbolic geometry come up with? We replace fifth postulate by this characteristic axiom. And this characteristic axiom says through a point not on a given straight line, there should be at least two straight lines through this point that are parallel to the given line, right? So we want to confirm if this is a correct model, if point cloud like this is the correct model, then you should see this axiom hold in this picture, right? So it turns out that if you look at the picture on the left, I give you the given line L, and path, and then I also give you a point A outside this this line L, and it turns out you can see the line M, and K. Those three lines are all parallel to L. They don't intersect L at all, but they all pass through A. So you can see that right now we already have at least three parallel lines passing through the same point A, which is they are also parallel to the common line L. So indeed, the characteristic axiom holds in this picture, in this model, right? But as you can also imagine that you can argue, you can definitely draw another parallel line passing A, right? So you can keep drawing, right? As long as it satisfies our definition for straight line. So you can see that taken at the very end of this, of the slides, I can essentially tell you the conclusion that it turns out that there will be infinite many parallel lines passing through this point A, which is parallel to L. We can actually draw infinite many. And you can now you can see that this is a totally different phenomena compared with the usual world that we live in, right? Usually, if in the normal sense of parallel, we already know that it should be at most one, right? You can only draw one anyway. But in this hyperbolic geometry model, things are quite different. And another thing is that we also, one thing which is different is the angle sum of the triangle. So how do we draw a triangle here, right? So it turns out that we use the common sense of triangle. Each side should be a straight line, right? Each side of the triangle. So on the right-hand side, you see the picture where B and C is a straight line. It's part of the straight line, right? So it's a line segment. And A and C is also the part of the line segment. And A and B is like an arc, right? Like an open arc, which is going to be part of the orthogonal arc. So it turns out that if you use three line segment to form the triangle on the hyperbolic geometry or in the point cloud disk model, as first we should know that one of the reason we like this model a lot is that it's what we call the conformal. Conformal means that it preserves the angle measurement. So preserved from what? From the usual sense of angle. So from an outside point of view, right, we live in the Euclidean geometry world, and we just measure the angle as we usually do. But it turns out that in this model, what we saw from the picture now, it's essentially the angle from Euclidean geometry point of view. But if you use the measurement from the point cloud disk model, it turns out that the angles will be the same. So it preserves the angle, which is a huge thing, right? And essentially, that you can imagine that if I give you a world map which preserves the angle in some sense, then it's going to help a lot for those people who like sailors on the boat, right? They need to make sure which direction they could go, right? If they are they want to go to the north or go to the south, then they need to make sure the angle is correct, right? So then you need to make sure that the angle is preserved in model. That's why we like this model. And if you look at this model, because the angle is the same as what we saw, so you can see that you have a 90-degree here and then another two very tiny angle. So we can add up the sum, and as you can see that this time the angle sum for the triangle is going to be less than 180. And as you can imagine, you can draw different type of triangle, and the sum is not going to be a fixed number. It's going to be like something less than 180, but it's not a fixed. It can be like 120 or 122, 112, like what you saw, or some other number. Okay, so let me see. I have a question here. If the intersection lies on the border or infinity line, would that be considered? No, right? Because the thing is that in the model, you should have every point should be within the disk, not on the boundary. The boundary is not included in the model. So you should not have a triangle whose vertex is on the boundary. Yeah. Okay, so now let's see. So I want to say that, okay, even though point colored disk is good in the sense that it preserves the angle, but of course it's a projection, it's a compromise, right? So something is ruined in some sense. So it turns out that the distance are distorted in this point colored disk model. And what does that mean for distance distort? It turns out that if you put an arc or a segment near the center of the disk, if you use the hyperbolic distance, then it will actually, in the hyperbolic distance, it will be much shorter than the arc, which is near the boundary. So let me draw the picture and show you what that means. So let's say you have a disk, right? This is the center. And let's say you have some arc, maybe here, right? Let's call it AB. Okay. And you have some arc here near the boundary. And that's say from our external point of view, right? We are living in the Euclidean world. We look at this AB and A prime B prime. Let's say okay, roughly I'm going to claim that right now I draw the picture where these two arcs have the same arc length from external point of view, right? From external point of view. Or in some sense, this is Euclidean sense, right? Because just look at the picture. Okay, maybe I should make it more precise, maybe like this. Okay, so now they look almost the same, right? So from Euclidean distance, right, we look at it, they have the same arc length, right? But if you use the hyperbolic geometry, if you use the hyperbolic distance to measure it, like if you put an ant who lives in the hyperbolic world, then it turns out that the segment who are actually further from the center, it's going to have the larger distance if you use the hyperbolic distance to measure it, right? So that's why that in some sense, that's why we meant that distance are distorted. So in some sense that if you have a segment which looks like the same size as the one that near the center, but if you're really living in that world, you will see that the distance for A prime, B prime is actually much longer. So how do you visualize or imagine this? Imagine that's why you're in some sense, A prime, B prime is closer to the infinity, right? So that's why the distance actually means larger when things are closer to the infinity, right? So if you think of the boundary as an infinity, right, then things near the infinity, of course, is larger. That's why that's one of the reasons we called it like infinity for the boundary circle. Yeah. So now if you can accept that, then you can see that that's one of the things that you need to be a little bit careful when you look at this such a model, because now the distance is not exactly what we saw here, right? So like if you put like two things which looks around the same size, in the hyperbolic world, those who near the boundary are actually means larger, right? So you need to be a little bit careful. And one picture which can actually describe this kind of weird phenomena very well is actually this MC Escher's like picture. You probably heard his name before. Like this is a very cool artist, and he actually explore this kind of concept about the distortion of distance for hyperbolic model in some of his picture. If you see, you definitely saw some of his work before where he has all the repeated weird like a multi-dimensional stairs or like all this kind of thing. You just Google MC Escher, you're going to see a lot of picture. And I believe like you probably already saw like one of his artwork, but one of the picture is this, essentially that he essentially take the phenomena I just described into account and drew this picture here. So how to interpret this picture is kind of cool. So it says, okay, you can see that there's a lot of like, I don't know, to me it looks like a bat, but like it says it's actually a demon and like an angel. There's some angel picture in between all the demon. So if you look at either the angel or the demons, that you can see that there's the one near the center are larger, looks larger, and the one near the infinity, the boundary, are smaller. So essentially, he wants to describe that from our point of view, it looks smaller. It's because it's near the infinity already. It's like imagine that you're on the earth and then someone walk further and further and further near the infinity, very far away. So it looks like as if it's become smaller, right? And then the things that if you look at the middle demon, but for someone who live in the hyperbolic world, to that person, the demon I circle first here and the demon here is the same object, right? Because to him, once he walk from here to here, for someone who live in the hyperbolic world, he could not tell the difference between these two objects. But for someone who are outside from the extrinsic, from external view, because he walked towards the infinity. So for me, it looks like it's further. So essentially, this picture kind of essentially incorporate that the distort distance behavior for the hyperbolic geometry. I think Escher also has another picture in the textbook that's also, I think they use a lot of fish, but it's a similar philosophy here. So, I mean, there's a lot of interesting thing that people draw a lot of like artwork trying to illustrate the hyperbolic like model here. So this is just, I mean, for some like information here. So, so after this model, I also want to introduce this another model. I would say this model, in some sense, it's good. Like okay, even though the distance is distorted, but at least it preserves the angle, right? But because it's on the disk, so sometimes it's not easy to work with, how to say, like arithmetically, right? If you want to calculate something or if you want to write down some equations, it may not be easy to do so, right? You can see, okay, the diameter is the straight line. Diameter is easy to describe. But another type of straight line is an arc, right? And it's an arc, which is also orthogonal to the boundary circle. I mean, I want you to write down the equation for that arc, it's actually hard to do it, right? It really depends on what's the size of the radius of that arc, right? So it's not easy to work with in some sense. But the second model I'm going to introduce here is another model for the hyperbolic geometry. And it's what we call the half plane. It's really literally, we are using the usual Euclidean upper half plane, right? So basically it just give you, like you say, okay, I have the half plane, right? If you think of that, you have X and Y, and everything inside is the points for the model. And where is the infinity? Infinity is the one on the x-axis. This is where the infinity is, right? So now essentially we consider everything which lies on the upper half plane. And that's the point we consider in the model. So that's what we call the Poincare half plane model. And now we need to think about what will be the straight line in this model. It turns out that there are also two types of straight line. First, and this is easier to work with because now I can tell you one of the straight line is all the possible, oops, sorry, too long, all the possible vertical line, right? So it's either the vertical rays start at the x-axis, right? And here, be careful because I don't want to include any points on the boundary, like on the x-axis. So that's why I put a circle here. So you can see that it's easy to describe it in equation, right? It's just x equals k, x equals 2 or x equals 3 or minus 2, right? It's a vertical line. And all the points for y is going to be positive because I don't want to include anything on the x-axis. So it's either this vertical line or actually any circle whose center is on the, any half circle whose center is on the x-axis. So let me show you a more precise picture. So you can see from the picture on the left here. So there are two type of line. One is the vertical ray. The other is the semicircle which center at the x-axis, right? So you can see that if it's centered at the x-axis and it's also semicircle, it's very easy to write down the equation once you know the radius and the center, right? That's why, like analytically, it's easy to work with this model than the previous point-Cayley disk model. And you can see that if I know the center is C, for example, like this M, right? Roughly the center is here. Okay, the center, of course, is not in part of the line, but this is the straight line, right? So once you know the center, maybe the coordinate is, I don't know, let's call it C0, right? And you know the radius R, then you can easily write down what's the equation for your straight line in this model, right? It's a semicircle. We know how to write down an equation for a circle. And if you want to solve for y, then if you take the positive square root, then that's an upper semicircle, right? So you can see that it's very easy to work with such lines in the hyperbolic model. And also now we can form we can also talk about what does that mean for like parallel, right? It turns out the idea, the definition for parallel here is pretty much the same as what we saw in the disk model. So for example, that you can see that L and M definitely intersect, right, at some point, right? And K and L, they don't intersect at all, right? K and L. I mean, one of them is a vertical line, the other is a semicircle, they don't intersect at all. So this is ultra parallel. And K and M intersect at this point at the infinity. And as before, we call this sense parallel. But we have a spatial situation that we haven't seen before, that if you compare K and T, they're all vertical line, even they looks like that they don't intersect. But actually in this model, we still call K and T to be sense parallel. So this is actually a spatial case, a little bit different than the disk model, okay? So then we can also talk about what's the advantage of this model, or in some sense, what's the compromise or sacrifice here. So it turns out that this model is good in the sense that it's also conformal. It preserves the angle. But at the same time, we are going to have a similar distance distortion, okay? Which means that if I give you a segment here away from the boundary, let's say it's like, it looks from our point of view, it looks 1 centimeter. And you have another segment here, also 1 centimeter from external point of view. But then if for someone who live in the point-Cayley half plane and live in the hyperbolic geometry world, this segment near the boundary, it's going to be longer under hyperbolic distance. Okay, so we have exactly the same distance distortion like situation than the disk model. Anything who actually near the boundary, the infinity, will be exemplified. Okay, so now we can also talk about triangle, right? If you want to form a triangle, then the 3 sides should be part of the straight line. So as you can see from on the picture on the right, you have this. So this BC, you can imagine it should be part of the semicircle, right? If you complete the semicircle. And you can also see that the AC is part of the semicircle, right? So they're all part of the lines, right? That's why they can form a triangle like this. So this is the point-Cayley, like the hyperbolic triangle. And as you can see, if you want to make sure to have 3 sides are both hyperbolic line, then the triangle is going to be thinner in some sense compared with the usual triangle in the usual Euclidean plane. So here in this half plane model, we are going to see the same situation where the sum of the angles are going to be less than 180. You can just draw the picture, then you will see this has to be the case. So now the thing is that I want to show you even more that so from now on, what we are going to do is, because we already saw that it's easier to work with this model because we can easily write down explicit the equation. So I'm going to discuss several phenomena using this half-plane model because I can really write down some equation here to work with. So the first thing I want to mention is that I can actually prove, or you can easily see it by drawing the picture, between any 2 points in this half-plane model, there always exists a unique hyperbolic straight line, right? So for example, now in this half plane, we know that it's either a vertical line or a semicircle, right? And you can just pick any 2 random points in the half plane, in the upper half plane. You can always connect them or join them using the hyperbolic straight line, right? So I want to show you explicitly, we can really write down the equation. So first of all, we pick 2 random points. So I just give the coordinate x1, y1, x2, y2. There are 2 several, that's kind of 2, 3 case, depends on how you view it. So the 2 main case is, depends on whether these 2 points share the x coordinate or not. If they share the same x coordinate, then the first picture will be, okay, you have A and B, doesn't matter which one. They share the same x coordinate, right? That's called it k, if x equals k. Then how do you join A and B? By using hyperbolic line. I mean, they're lying on the same vertical line. So the hyperbolic line that join A and B is just the vertical line that we talk about, right? So we just can easily write down the equation. So x equals k is the only hyperbolic line that can pass through A and B, right? If this is the picture, you cannot really find a semicircle passing through A and B because they essentially lies on the same vertical line, right? I mean, you cannot find a semicircle join A and B at all, right? So you can see that this is the easiest case. So for 2 points A and B which share the same x coordinate, you can find a vertical line, which is one type of hyperbolic line that join those 2. But then you may ask, what about the other case, right? If it's, then the other case we can consider is when they have different x value, right? Then we need to do a little bit more work. But as you can imagine, if they are having 2 different x value, you can definitely find one unique semicircle that join those 2 points. Okay, so first of all, this is the case 2. If the x coordinate are different, I claim I can still find a unique semicircle join those 2 points. And this semicircle is going to center on the x-axis. And under this case 2, technically for like analysis point of view, I want to show you explicitly how to really find such circle, right? I really can ping, if you give me the coordinate for 2 points explicitly, right? I can definitely find you explicitly the circle. It's actually not hard to do it at all. And here under case 2, I want to distinguish into 2 separate subcase. One is when both of them have different x coordinate and also different y coordinate. So what does it looks like, right? So I'm just going to draw you a picture. So let's say if I have A and B like this, right? Okay, so now these 2 definitely have 2 different x coordinate and y coordinate, right? So let's just say this is the xy plane. Okay, so now how to find such circle that's going to semicircle that's joining A and B or passing A and B, right? So to do that, first you connect A and B. I want to tell you the picture, like show you the philosophy, how to do it. Then I can show you a more precise formula. So first you connect A and B. And as I mentioned here, you can find the slope of AB, right? And since they don't have the same y coordinate, so they're so the slope is not 0, right? Because they're not horizontal. Okay. So now how to find the semicircle, right? So the idea is the following. Oops, sorry. So the idea is the following, that okay, I first draw you like a rough picture, then I will tell you how to find the circle. So let's say if I want to have a semicircle centered somewhere here, right? I don't know what the coordinate is. But if I want to have such circle, it should roughly look like this, right? Now the question is, how do I identify or locate the center? So one thing you can do is that AB now becomes a chord of my circle, right? then I know that if you can find a perpendicular bisector of this chord, it's going to pass through the center, right? This is something we learned in, I think, chapter 10, right? Like we know that if I have a chord AB, then the perpendicular bisector of this AB is going to pass through the center, right? In some sense, this is very intuitive. So we want to find such perpendicular line. And since it's the perpendicular bisector, so it's going to pass through the midpoint of AB. If you give me point A and point B explicitly, the coordinate, I can easily find the midpoint, right? So now the thing is that, okay, if I have the midpoint here, then this is A and B will be known and M will also know. So now the question is, if I call this line L, this perpendicular line L, I can also find the slope of such line, right? Because I know M, the line M is, if I call this chord M, right? Let's say if the chord is this, I know that if I already know the slope for AB, then to find perpendicular line, then I know that they're going to be, the multiplication is going to be -1, right? The slope. The slope of M times the slope of L is going to be -1. You might know this from calculus, you may not remember, that's fine. But this is one way we find it out, right? So if you know that in this case, if you look at the picture, you know that the slope AB is negative, let's say it's -2, then the slope of L is going to be 1/2 because both of them multiply to be -1. So now if you know the slope of M, this AB chord, you can definitely find the slope of L. You know the slope of L, you know it passed through the midpoint. You can write down the line equation. Once you can write down the line equation, you just find out where it intersects x-axis, which means once you have the line equation, whatever the line equation is, you plug in y equals 0. That will give you the center of the circle. That's how you find the center. That's essentially, I tell you the whole scheme behind it. Okay, so which means that if you can just give me A and B, the coordinate, I can definitely find you such circle. So I'm going to show you the formula. I don't want everyone to memorize it, but rather you should understand why this work or why that makes sense. So, okay, so the perpendicular bisector of AB has the slope, the perp, right? This is the slope for L, which is the negative of the original slope. Okay, so this is essentially M perp times M equals -1. That's essentially what we have. And we have the midpoint, right? So this is what I just said. You need to find the midpoint. Then the perpendicular bisector, the line L, has this equation because it passed through the midpoint, have the slope and perp, right? Once you know the slope and the point, that's a point slope formula, right? Then how do you identify the center of the semicircle, right? Then it's essentially the intersection of the line with the x-axis. And actually you can really, I already tell you here, this is the formula, right? You can solve it and see the formula is simply the midpoint, the x coordinate for the midpoint plus the original slope M times the midpoint, the y coordinate for the midpoint. So you can really make it a formula. Okay, so I don't want you to memorize, but just to tell you, you can really find it. Okay, so this is not too bad. This is the worst case in some sense, but from the picture, you can see there's a systematic scheme we can follow. And another thing is that then once you find the center, then you can easily find the radius, right? So once you find that, okay, it passed through the A and B, right? And this is the center, right? Then what would be the radius? You just find the distance either between CA or CB, any one of it, right? Here I pick C and A, essentially. Then that's your radius. So what I'm going to do for the problem from this part is just, I will show you some example. I will give you maybe a more like a computation problem, and just to hope you to follow the scheme and then found the straight line passing through 2 points, and that's it, right? I don't want you to memorize the formula, but rather knowing how to use it or how to identify what information you need or you have. And another case would be easier in some sense, while if they share the same y coordinate, right? Then in the picture, it's much easier in some sense. So if you have 2 points A, B share the same y coordinate, how do you find the semicircle passing through? Then you can imagine that, okay, I'm going to maybe draw like a rough circle, right? Semicircle pass through AB. Same idea. You connect AB, but now you already know that what's going to be because now the slope is 0, right? So we're not going to do exactly as the previous case. But this one is easier because you know where the center is. The center should lies on the perpendicular bisector as well, right? And it's right at the middle, right? So you can easily see that this is the midpoint, right? So the midpoint is essentially the x coordinate is x1 plus x2 over 2. And the center is just on the x-axis with the same x coordinate as the midpoint. So right away, you can tell me the center is really have the coordinate, x coordinate, x1 plus x2 over 2. So this case is much easier than the 2A case. So, but the idea is the same, right? Once you join AB, you can identify where the center is. So this is doable explicitly, okay? So now we essentially tells you that if you give me 2 points in the model, I can find a unique hyperbolic line join them. And the next thing I want to show you for the second half of the slides is that it turns out that the reason we call a semicircle or a vertical line like this to be the hyperbolic straight line is that it turns out that if I join 2 points using hyperbolic line, it's going to give me the shortest path under the hyperbolic distance, right? If you go back to think that how do we define straight line in Euclidean plane? The straight line usually we meant that is the shortest path connecting 2 points, right? That's why we know the straight line in usual sense. It's walking from, let's say if from point A to point B, what's the usual straight line? It's really just like a straight line, like a no curved line in some sense, right? How do we know it's a straight line? It's the shortest path, right? So it turns out that we later on, when we know how to calculate the hyperbolic distance, or essentially I should say, to be more precise, hyperbolic arc length, I can show you that it's the shortest path. And the shortest path is guaranteed by these two types of hyperbolic line, either the semicircle or the vertical line. So I want to show you this example. This is exactly some type of the homework problem I'm going to assign you for this type. So I give you points A and B like this, right? You can find the slope, and this is the slope of AB. And I can find you the midpoint, right? Then essentially by using the formula we gathered before, we know that the center is going to be this just by plugging the formula, right? And then the radius is going to be the distance between either the center and one of the points, right? So essentially, if you want to do the real like calculation, so this is like 1, 1, right? And 2, 4, right? 1, 1. So let's say this is A, this is B, right? So what you're going to do is, okay, I'm going to join AB, and this is slope 3, and I'm going to find a straight line. And then whenever it intersects, this is the center. So you can see that what's the center here? It says it's 9, 0, right? Roughly correct, right? And you can see what's the radius. The radius is going to be, I think they use C and A, right? So this is going to be the radius. So I'm not going to redo it because I want people to go back later on when you have time to read through some part, then you can understand the scheme more. But I just want to show you that we can do such example. Once you know the center, once you know the radius, you can write down the semicircle. So the semicircle is roughly like this. Oh, actually, no, it's bigger. I have a center here. Actually, I need to draw a very precise picture, something like this. Right? I cannot finish it because it's too large. So you can actually find the precise equation for your semicircle, okay? So this is doable once I give you like just 2 coordinates, and you need to do a little bit calculation to get this equation for the semicircle. So now I want to talk a little bit about the arc length because I want to show you at least how to calculate the arc length in hyperbolic plane. But first, before we do that, I want to recall this is arc length formula that everyone saw in Calc 3. Okay, so this is how we calculate the arc length for Euclidean plane that we usually know of, right? So what's arc length, right? If you have point A to point B and you have a curve, right? You can really literally calculate what's the length of this curve, right? From A to B. And to calculate that, you need to give me the parametric equation for this curve. So like you will have an equation for X and Y coordinate, and it's going to change along the time, right? And then you take X prime and Y prime, take the square of it, take the square root, integrate it. This is the arc length formula. If you have the parametric equation like this, right? This is something you saw this before in Cal 3, maybe a while ago, but you definitely know how to calculate the arc length. And by knowing the arc length formula, it turns out that we know a Euclidean straight line, the usual world we live in, the straight line between 2 points is the shortest path. What does that mean? It means, okay, from A to B, the shortest arc length is the one that when you connect them by really the straight line in the usual sense we know, which means the arc length of this straight line would be shorter than any other curve join A to B, right? So the middle the middle straight line is going to be the shortest path under the Euclidean arc length, right? And we actually managed to find out that the usual Euclidean distance between 2 points is really just this formula we usually know of. And this is the shortest, coming from the shortest distance from A to B, okay? But now, of course, if we moved from the Euclidean plane to hyperbolic plane, then things will change, right? The way we calculate the arc length would be different, right? Because remember, even we are in the half plane, the distance, the sense of distance is different than we usually know of. It's distorted, right? So we know that in hyperbolic plane, everything near the boundary is longer. So we need to take that into account, right? So the thing is that for Euclidean plane, everything is like the same, right? But in in hyperbolic plane, if you go near the x-axis, if your y coordinate is smaller, everything is actually larger in hyperbolic model. So we need to, in some sense, compensate that, right? We need to incorporate with this fact. So this brings us to the following formula that it turns out that the arc length in Poincare half plane is calculated in this way. So you can see that the only difference between this model and the usual Euclidean model we know is that we multiply this 1 over y, right? You can see that if y coordinate is smaller, then the whole thing is larger, right? So this essentially correctly reflects the fact that everything near the boundary or near the x-axis is larger. So this is already we calculated, we know, like we need to prove that this is the formula, but I kind of tell you the fact here. So this is going to be the arc length for this model. That's why I put it as sub h. It's for the hyperbolic, for half plane model. Okay. So if you want to do a practice, you can see, okay, what will be the hyperbolic arc length for the same path, right? So this is a linear path. So what I'm doing here is that I'm using the same point here. So I'm having 2 points, one from 1, 1, the other from 2, 2, 4. So because you can see that this essentially is a linear path. So I'm really describing the line here. Okay, the straight line. But if you calculate the distance between 1, 1 and 2, 4 along this line, using hyperbolic arc length formula here, take into account this 1 over y. You can see that you're just plugging in, right? This is the y, the penetration for y, and this is x prime squared, y prime squared. You really calculate it. It turns out that you can see that you have this weird log here. This is different. The distance will be different compared with the usual Euclidean distance, right? And as you can imagine, things near the boundary will place bigger effect in some sense, will be longer. Yeah. So now the question is, I kind of already tell you the answer. What is the shortest possible path between 2 points in the hyperbolic plane? First of all, the shortest path usually in geometry called the shortest path to, we have this more formal definition. We call it geodesic, okay? And it turns out that, as what I just tell you, the shortest path is a unique one. And then the shortest path is actually, however you can connect it using the hyperbolic line that we talk about. It will be part of the semicircle that we just find out, or part of the vertical line. And this is what we call the hyperbolic line segment. And we actually just proved in some sense, right, explicitly, if you give me any 2 points in the hyperbolic half plane, I can always connect it using either semicircle and or vertical ray, right? And there's only one unique way to do it. That's why there's only one unique shortest path. You might ask me, say, oh, is it always true that in all different kind of geometry, there's always one unique path? It turns out it's not true. Later on in spherical geometry, you're going to see that it's possible to join 2 points by different paths, but they all have the same shortest distance. It's possible, depends on what geometry you're talking about. But at least for hyperbolic one, in this case, we only have unique geodesic join 2 points in hyperbolic half plane. Okay, so that's in some sense, hyperbolic geometry is also good because it's more certain in some sense. There's no complexity here. Whereas if for people who actually study geometry for sphere, they always hate sphere in some sense because sphere has more exception in some sense. Okay, so in the last 15 minutes, I want to see how much I can tell you. So let's do this. I don't want to show you all the detail, but at least what I can do is to really calculate the arc length, or essentially the length for those 2 type of hyperbolic line, right? So we already know for hyperbolic, for Poincare half plane, there are only 2 type of hyperbolic line. First is the vertical line. I mean, to calculate vertical line, it's not too bad. Second, it's a semicircle. But keep in mind that the distance we use, the arc length formula we use is different now, right? We need to incorporate into this 1 over y effect. So let's say if I have 2 points here, A and B, let's say I want to find the length, the arc length or the length of the hyperbolic segment that join those two. So first case is when they share the same x value, right? So then this is what we know, right? Then if they have the same x value, then we know that there's only one such hyperbolic line join them. It's the vertical line. And we can parameterize it using this penetration. You definitely heard this fact before in Cal 3 that arc length is independent of penetration. For the same curve, same trait, same trace, right? You walk from A to B. So for example, this is A, this is B, right? As long as you're on the same trace, on the same route, it really doesn't matter how you parameterize it, right? Parametrization is like a description, right? You can walk from A to B along this vertical line in faster speed than I am, right? So then how you parameterize it might be different. But as long as you follow the same track, same trace, then the arc length should be the same. Okay, this is same thing everywhere. Okay, so I can just choose one possible penetration. So in this case, I choose x to be fixed because I mean it's a same coordinate, and y I choose it to be t. Right? You can choose to be, I don't know, t squared or whatever, as long as it fits the trace. Then we can calculate the arc length, plugging into the arc length formula. So you can see that this is the 1 over y, right? 1 over y. And inside is really just x prime squared plus y prime squared. And you do the computation. And that's where the log that you saw in the previous problem, that it's going, if they share the same x coordinate, you're going to see, actually, even this is not the case, you're going to see some kind of log because you're integrating something like a 1 over y, right? And in this case, because I want the distance and I also want to take into account possibly maybe y1 is larger than y2 or the other around. So I actually, the final formula I should use is essentially, I'm taking the app's value here. Depends on whether y2 or y1 is bigger or smaller, right? So you can see that I just want to show you the formula. I don't want everyone to memorize it at all, but at least you can see that that's why the log, where the log come from. And what about the second case when they don't share the x coordinate? Then we are going to have a semicircle, right? So if you're going to have a semicircle, we're going to parameterize it first, then plugging into that arc length formula, that the one that was 1 over y. So first of all, between A and B, I have this hyperbolic segment, which is a semicircle, like an arc, right? Part of the arc. And I can parameterize it using this penetration, right? This is kind of how you deal with the polar coordinate a little bit, right? So if you parameterize it, then you describe how the path from A to B works. Okay, you're describing this path, okay? And also I need to tell you what's the starting angle, which is alpha, and then end at beta, okay? Then I'm just going to show you the formula. It looks very ugly. Please do not memorize it. I just want you to kind of know that we can derive it. So I'm plugging into, this is again 1 over y, right? This whole thing is 1 over y. And the inside the square root is just the x prime squared plus y prime squared, right? And then take the square root. So just directly calculate it and using some like trig identity formula we know. Again, you can see that you're going to have log again. Okay, so it really doesn't matter whether your straight line, your path is like vertical line or like semicircle, you're going to see the log anyway. And actually the last slide is just to tell you, you can turn the distance back into the things related to the coordinate. Okay, so I'm not going to explain much. I'm just saying that if you know the coordinate of A and B, you can actually calculate the distance in terms of the coordinate of A and B, and also related to the center and the radius of your semicircle. So there's a way to formalize this thing, but at least we know how to calculate it. So I don't have time to like really directly show you everything, but I just want to tell you the fact. So I'm going to just glean through very fast the formula. Please bear with me, but I don't expect you to understand right away, but I can give you all the information here. So later on, if you want to even make sense more detail, you can come back to it. So the first thing I want to say is that in this half plane model, it turns out that the hyperbolic segment, either the vertical rays or the part of the semicircle, is going to be the unique geodesic, which means that I need to prove you that, for example, I say, okay, I have A and B, right, in the hyperbolic plane. Okay, to connect these 2 points, we can draw a straight line, right, connecting these 2 points. So this is the curve between straight line, okay? But I can also draw other curve connecting A and B, right? Or maybe even the straight one, right? It turns out that under hyperbolic geometry, right, under the hyperbolic arc length, the part that comes from the hyperbolic straight line will give you the shortest arc length. Whereas even if you give me the usual straight line that in Euclidean sense, it's not going to be the shortest one under hyperbolic model, right? Not mention if you have something even more curved. So it turns out that we can prove if you give me all the possible paths between A and B, the shortest one under hyperbolic arc length, it should be the one which comes from part of the hyperbolic straight line that we defined at the very beginning. It should be either part of the semicircle or part of the vertical line. Okay, depends on the relative position of A and B. So you can see that this is exactly what I said. Any path between A and B would be longer than the path either along the vertical ray or the arc. Okay, so essentially what I'm going to show you here is just really the proof, which I don't want to show you now because I don't have time here. So I just want to glean through it. I just go over it. this. So I just want to jump to this final 2 slides here. So it turns out that in summary, if you have two, this is exactly what we just calculated, right? If you have two points here, which share the same x coordinate, then the distance between A and B is the shortest path connecting them, right? So essentially, if you have 2 points here, right? So if you have 2 points A and B, which share the same x-axis, then what would be this hyperbolic distance? The hyperbolic distance would be the arc length for this segment. And that's what you saw here. If you don't have the same x coordinate, so maybe like A and B is like here, then the distance is what? The distance is the arc length of part of the arc. And using the hyperbolic arc length, which will give you this formula here that we calculated earlier. Okay, so we have to use the hyperbolic straight line or part of it to get us the shortest path. And that's why we define the distance. When we say distance, it always means the shortest one between 2 points. Okay, so that's essentially the summary. So essentially, I think some of my, maybe few of my homework problem for 12 is going to be the using some of the formula here, right? So you have the formula to refer to in the textbook. So my purpose is not just for you to plug in the formula, but rather to kind of understand that why this is the case, why we see log here instead of the usual Euclidean length, right? It's because when we calculate the arc length, there's a 1 over y effect that we need to take into account. So the last thing I want to show you, let me just show you like some. So it turns out that if we assume Hilbert's axiom, right? Because we know Hilbert's axiom is just like essentially to make sure that to actually improve the Euclidean axioms. So if we assume Hilbert's axioms, but we replace the parallel axiom by the characteristic that we know, right? I just restated the characteristic. Then that's how we got the hyperbolic like geometry axioms. And if we replace the axioms of continuity and replace it by Dedekand's axioms, I'm not going to explain this, but I'm just to put it here for completion of the information. If we replace by the logical equivalent axiom, what we're going to have, the outcome for hyperbolic geometry is what I actually stated a little bit earlier, I think on Monday, is that it turns out that in hyperbolic geometry, all the parallel lines are not everywhere equidistant, as you can see, right? Like if you have some parallel lines, these two, right, along the hyperbolic, every point on the line is not going to be equal distance, as you can check, right? And also, the sum of the triangle, the angles of the triangle is less than 180. We already kind of observe it. So this is true for any hyperbolic geometry model. Doesn't matter whether it's disk model or any other model, as long as it represents a hyperbolic geometry model. So the final conclusion I want to show you is this exactly what the thing I taught in the beginning. Through a point not on a given straight line, it turns out that there will be infinite many straight lines parallel to the given line, not just two, right? We start with say that it should be at least two, but it turns out that if we put up all the axioms together, we can prove, actually we kind of already see it in the picture, in the model, right? In the disk model, we can draw so many parallel lines through the same point. It turns out that this is actually a very special feature in hyperbolic geometry, that you're going to have infinite many lines. Okay, so yeah, I think that's the end. So I skipped some of the things, but I definitely will put all the things together. So this is just to give you some survey in some sense that there's some kind of weird geometry that we usually cannot picture or imagine using our usual sense. And to come up with it is just really simply by replace one axiom, right? The fifth postulate, then we create such a different axiomatic system. And this type of geometry is still consistent and valid, and you can somehow use 2 or 3 different kind of model trying to make sense of it. But the reason make it harder is because that we you cannot really directly draw a correct model other than this type of distance distorted model. Okay, so I'm going to tell everyone the plan. So I only have limited time in like essentially coming back on 30s. So what I'm going to do is the following. So next Monday, Wednesday, it's the presentation, I know, but depends on like how many time that people use on the presentation. I'm like, for example, for people who are already scheduled on the 30s, I would not push you forward. But for example, let's say if on Wednesday, next Wednesday, if people finish earlier, I would probably just like use the remaining time to talk about some like other type of model, because I want to at least give you some glimpse of spherical geometry and taxi cab geometry, because these are the other two different type of model. But I know that we don't have much time left, so I would see how much stuff I can show you. And coming back on 30s after the break, I'm also going to use the remaining time after the presentation to show you some other things. But as you can imagine, it's very close to the exam. So for hyperbolic geometry, spherical and taxi cab, I'm not going to test you much. I will be very specific, tell you what things I'm going to test you. It will be very limited. It's pretty much more or less like definition type of questions, like property type of questions, right? I'm not going to ask you to do all this computation, the ugly formula I show you. That's impossible. Okay, so if any question about homework or presentation or anything, feel free to stay. And have a nice weekend, early weekend.
Yeah, I just have a question
sure.
about my presentation.
Yeah, sure.
I didn't know if like you have time right now to answer it, or if we could set up a time.
So
like,
you want to
maybe-
show me something, or like your answer, or what, like specifically what type of question?
Specifically, I just have a couple of questions about what is, I guess, allowed. I'm trying to remember like what we can and can't do, and I just wanted to make sure that my steps were accurate and like acceptable.
Okay, so probably I would prefer that, because the thing is that I'm worried that if you ask me on the spot, I might miss some details. So I like to be safe, right? I want to have some time to think through it before I can answer you complete. So so what I would do is that if you already have the, I don't know, some written things like you want to show me, could you please like scan it and then send it to me so I can look over it in the next 2 days. And then if you want to talk about it, then yeah. And essentially when you send an email, we can also set up a time through the email. Maybe like, I don't know, like today's Wednesday, maybe it's tomorrow or Friday, probably Friday. Then before Friday, I should have some time to read through it. Then we can talk about it, because that will give me some time to read through the things, so it will be more correct. I'm worried that if I answer on the spot, I might make mistake. Yeah.
Okay.
Yeah.
Can I think this is a fairly simple question.
Yeah.
In mine, it has to do with squares. I'm doing one of the Pythagorean theorem ones, and
okay.
there's a square, and I'm trying to recall if we're able to say that a square is a parallelogram.
No, the definition is not really included. Let me see. Square. Okay, square. The definition is to. If you only talk about just the definition of square, the definition is every angle is 90 degree, right angle, plus all the sides are equal, right?
Yeah.
As you can see that it does not involve anything about parallel.
Yeah. So
but we can prove it. Yeah. So we can prove it. You can prove it that it's going to be. Actually, from the angle, you already know that it's going to be parallel, right? Because every angle is 90 degree, right? So if you have two sides, right, you can see that because the what's that called, the like the same angle, interior angle on the same sides is add up to 180, right? So there's a proposition tells you. So let me just draw you a picture, then it will be quick. Give me a second.
Okay. No, I know what you're talking about.
So you can see
I was just going on the path of like, there's a proposition like 1.46 talks about how the lines are parallel by construction. like it's a construction problem, I believe.
Oh, you mean to construct the, no, I think that's just only allows you to construct the square, but it doesn't
Okay.
really tells you is it parallelogram or not. So I would say if you want to, I don't remember exactly which part that you really need to say it, because I don't remember at all like what's the detail of the problem. But if that's say, if you just based on what you tell me right now, say you have a square, right? And I know this two angle will be 90 degree. So I remember there's a proposition, I don't remember the numbering, but if you have this angle and this angle add up to be 180, then it should imply these two lines are parallel.
Oh yeah, okay.
Yeah, so there's a one proposition. I think even earlier, I think it's maybe in chapter 3, I believe.
Yeah.
Yeah, one of the very early propositions. So yeah, basically, I would not say it's in the definition of the square where it's a parallelogram, but you can prove pretty much right away that it should be a parallelogram. Yeah.
Okay. Also, as for like, if things are congruent, does that make their area the same?
Yeah.
Is that something that
Yeah.
we know?
Yeah, we know. Yeah, if two say triangle or two quadrilateral, if you say that they're congruent, then they should have the same area. Yeah.
Okay. Can is there like a proposition for that, or is it just kind of like,
I think that's one of the
knowledge?
Yeah, one of the, I think I need to find it like somewhere. I think it's one of the axiom we use in the area axiom. Let me double check. Yeah, I mean definitely we can use it, but I want to see whether I can pinpoint where it is. So actually, at least it says that in the I think in the chapter 3, like sorry, not chapter 3, chapter 7.3, like page 136, like one of the the area axioms we kind of use it for free is that the congruence postulate, that you can say that if two triangle region are congruent, then they have the same area. That's one of the kind of the postulate there. Yeah. But of course, if you talk about like a polygon, right, then but technically all the polygon, you can break it up into triangles. So I would say that if I remember correctly, the problem you pick or you register is more like an algebra problem.
Yeah.
So there are a lot of things you could definitely take it for granted for sure. Like all the area things that we know of now. Yeah. So can you remind me which problem is that? Like I remember there were two problems.
It's the first, it's task number 1. It's page 156, number 8.
8. Okay, so let me see. Right triangle, construct this or something, construct that. Okay, first part you prove it congruent. Okay, that's a geometric way. And prove that lies in a straight line. So you prove the angle add up to be 180. And prove that quadrilateral are all congruent. And here, we haven't really covered it, but you can see that I said that you're allowed to use this weird quadrilateral X like congruence scheme SAS. Yeah, so you can take it for free. You don't need to justify. You can directly use it. Yeah.
Okay.
And then so then you can see that once you have congruent stuff, then you will have several. I think the hexagons A, D, E, F, G, C will looks like, I don't know, some quadrilateral plus triangle, I guess, right? Or maybe two, and then if they all separately, individually congruent to some other things, then their area will be, so you can directly use that. If you have this congruent quadrilateral, then the area is the same. Just take it for granted, that's fine. Yeah.
Okay. So yes, we can say that the areas are congruent.
Yeah,
of the hexagons.
If two things are congruent, then they should have the same area, but not the other way around, right? If you have same area, it may not be congruent, right? So it should be congruent, implies the same area. Yeah.
Okay. And then last real quick question. As you can see on this one, there's a lot of like redundant steps. Like we have to do, we have to prove the different quadrilaterals with SAS,
Mm-hmm.
like 3 different times. I was wondering if you wanted us to prove those all, or say like if we explain the first one with detail, like a lot of detail, and then the other two we explain like this is equal to this by similar steps.
Yeah.
Like
So
explain it, but without saying like postulate this, like proposition that, like just saying that this is by similar steps we have the same thing.
yeah, that's fine, because the thing is that like depends really on how you present it, because I remember that last year whoever present in for this group, what they do is that they I mean, I don't know actually how they do it, but I roughly remember that they present some picture and then they show it the shaded parts when they compare the congruent. So it helps them a lot to save some steps, right? They didn't really write down line by line, but rather they write down something, right? And then they do like a picture comparison, so it's easier for them. But of course that I know what you mean. That's why that I said that the presentation usually will contain much less detail than the written part. So yeah, I'm fine with what you said, that if you could show just one of them, like a one case, like in more detail, the other you can probably say that, oh, by similar steps, you can, I don't know, maybe just show some, maybe say it, or like show some, like depends on how you want to do it, right? You can directly show less detail, but just kind of bring it, like roughly touch it, and then that's fine. Yeah, because I can
Okay.
understand that there's no way, definitely no way you're going to show every single case like super in detail, right?
Yeah.
So you can, if you can do one case like carefully, the other is more or less you just kind of touch it. Like for example, if you're comparing two things or the other things, what would be the similar like evidence, you just kind of touch it and go, that's fine. That's why I
Okay.
didn't really precisely written in my instructions say, oh, how, like, because I kind of rather want students to decide for themselves that how do you want to present it, right?
Okay.
And then just, but yeah, so I would say once you decide maybe how much one way, then to be safe, you should definitely rehearse it, right? Do a real presentation, time yourself, right? And see whether you can, because before you really practice it once, you would not know exactly how much time you're going to spend. So
Yeah.
you should try and see, like even you say that like present this much maybe like detail, later on when you, after you rehearsal, like do a rehearsal, you might change your mind, right? By
Yeah.
showing even less or something like that. Yeah. But if you're not sure, like after you have some slides, you can show me over the weekend as well. If you're not sure that is this okay or not, I can glimpse through the slides you use and give you some suggestion if you want. Yeah.
Okay. Okay, thank you.
Yep. Uh, yeah. Okay. So any other questions for anything? Presentation, homework?
I think I have a quick question on